Transformers. From very start of this course, we always promise to talk about the electric machines and how they have been used or controlled. But what are the use of transformers? Why we need to talk about transformers here? In fact, transformers are very important and very dear to our electrical engineers, especially power engineers. And we can find many of them in different rating and different settings and different size in the power system, almost everywhere. So if you come across some electrical system, there is a very high chance to one way or another you have to deal or come across a transformer. In fact, transformers have been in the picture and very important for us from the very start. The reason that nowadays we have AC systems, not a DC system, is partly due to transformers. I don't know if you have heard this story or not, but more than 100 years ago, there was a big fight, they call it a war, between two companies that they want to try to have electrical systems in North America. One belongs to Mr. Edison, tried to have DC system. The other one belongs to Westinghouse, wants to have the AC system. But this war was belonged and was won by Mr. Westinghouse because of one genius engineer that he has, that we know it as Mr. Tesla. And the main thing that let them won this war was transformer. Transformer, all of them, to transfer the energy or long transmission line with high efficiency. We are going to see that. We are going to see how these transformers can do this for us and why they are so important. And if Mr. Edison wants something, really, it's going to be very hard. You know, the rumor has it he has even killed to get hand over some kind of patent. So he has done everything that he can. He even in make electric chairs to show AC system are very dangerous. He didn't win the game, but later we used the electric chairs in a judicial system for a long time. But anyway, enough of the story and history. Let's go and talk about the more technical parts. So, transformers, in a way that we more know it in the physical way, is something like that. So it's usually essentially two or more windings that are magnetically cooled. In many cases, this magnetic coupling is done through some magnetic core, like the figure that you can see at right. But there are cases also that they are cooled with non-ferromagnetic material, usually by air. So, but we have two kind of transformers. The one with the ferromagnetic core, they usually called as iron core transformers, and they are for high power applications usually. At the other hand, these air core usually are used in low power cases because of poor coupling, mainly in electronics. In this course, we get focus on these high power situation scenarios. We are not interested in the other ones, but don't get confused or shocked if you hear that there are some transformers coupled by air. But the more realistic figure of these transformers is something like this in the real world. These are some single-phase transformers, and we have it here in the product too. If next time you're walking in downtown, take care about the poles, electric poles that we have. These are some pole-mounted single-phase transformers. You can see them inside Toronto too. I think nowadays they don't use this sad black colors very much, and they use more gray colors for them, grayish colors. But you can see them even nowadays in Toronto. So what are the main applications for the transformers if try to talk in more general case? So there are four main applications for transformers. One is power transfer from one AC system to another at different it's called desired voltage or current levels with or without isolation. Example is step up, step down, or step up transformers. This is the application that Mr. Tesla has used. For a step down or a step up the voltage and current, for transferring the energy over the long transmission line. If we can step down the current, because the losses are related to Ri2, Ri square, if we can decrease the current, we can decrease the losses for a long transmission. So they decrease the current, and instead of that, increase the voltage and decrease the current. They go to up to 400 kV voltages for long transmission line. And this is the main application that we are going to talk about it. So in generators, which are usually far away from the load, there are some dam or some offshore wind in the ocean. If we try to transmit power at the same voltage and current that is generated, we are going to face lots of losses. That was the problem 150 years ago. So the solution was to use this transformer, decrease the current level, and now transmit them over long transmission lines. And then when we get close to the load, we try to step down the voltage and increase the current in several steps. What is the voltage in our homes? Pardon? 120. But it can go up to 400 K in transmission. So all of that happens because of transformers and high efficiency that they can provide for us. But we also said with or without isolation. What is that? You see, we have two circuits here. Is there any wire connecting them? They are isolated, no wire coupling between them. So it's like that these two circuits are completely decoupled. So it has its own benefit, though in power systems sometimes we don't need it and we don't use this coupling. But it results in another application, signal transmission with galvanic isolation for safety reasons. Sometimes we want the circuits becomes coupled, no wire connection between these two circuits. That's where we use transformers. No step down or step up the voltage is needed, just coupling, decoupling in fact. So one example is in biomedical equipment. Another application that we are not very much interested but is very much used, and we will see some example of that in this course, is load matching and power transfer maximization. So it's usually used in communication system. So sometimes by using these transformers, because we can change the level of current and voltage, we can assure to maximize the power transfer. We will understand that much better later in an example, but it's not the cases that we are interested in this course in general. Finally is instrumentation. Oh, no. It's for voltage or current measurement when direct measurement are unsafe or infeasible. Consider it the transmission line we talk, 400 kilovolts, and you have a microprocessor. You want to control them. You want to measure everything and control. You cannot connect a microprocessor with input of 5 volts to such 400 kilovolts for measurement. So you use a transformer to decrease the voltage from 400K to 5 volts, then change this analog voltage to digital, and then you can feed it into your microprocessor and do the control. It's how it's happened in the substation in the power system. In fact, we use lots of them. And we have even separate name for them. We call them CT or PT, current transformers or potential transformers. But this is not the case that we are interested in this course. But we cannot go ahead and use this physical structure everywhere in power system, in electrical system. We cannot just draw this figure with all the core and lamination and all the winding. So we try to come up with symbols. We already use lots of symbols in electrical engineering. So we have symbols for the transformer as well. Here, this one is single phase transformer without a ferromagnetic core. So we show the two windings like that, and this is symbols of a transformer. For adding the magnetic core, which is the cases that we are interested, it's simply adding these two lines. They represent the ferromagnetic core have been used. So here we have single phase transformer, this time with a ferromagnetic core. And most of the time in this course, we are working with this symbol. We are going to improve it a bit later, but basically we are working with this symbol. But these are not the only symbols that have been used for the transformer, especially in the power system engineering. There are other symbols. You can see them as below. We are not going to work with them, but I think it's a good idea to introduce them to you, not get shocked if you saw them somewhere. So these are usually single line symbols, usually used in power system literature for large three-phase power transformer. So you know, in power system, in electrical system, we are not single phase. We usually are in three-phase system. I'm not going to talk about that. It's much more complicated here. But we don't go and draw all of these transformers for each phase usually. Even most of the cases, we don't draw three lines for the three phase. We are very much interested in what we call it single phase diagram. Single line diagram, one line representing all three lines, and using these symbols to represent three-phase transformers. But these are not the subject of this course. Just don't get confused if you saw them somewhere. Any question up to here? No? Perfect. Okay. I think enough of the symbols. Let's get closer to some modeling. We want to know how to model, how to understand these transformers. But before going to that, let's make some assumptions. Let's start with the easiest case. Let's assume that we are working with an ideal transformer. And then we can come back and revisit our assumptions. See what we have made here, which of them is practical, we can keep them, and which of them we need to improve them. So at the start, we start with the ideal transformer. In such an ideal transformer, the windings are ideal, the core is ideal. So what are the main assumptions that we are going to make? First of all, we have some windings here, and we know the windings have resistance. For sure, there are wires. So we have one winding here, another winding here. But for a start, we say, okay, let's forget about that resistance. Let's assume there is no resistance. So windings have no resistance. The second one, we assume we have an ideal ferromagnetic core. What does it mean that we have an ideal ferromagnetic core? What will be the impact? How we can model it? Any idea? Even zero reluctance. So we have infinite permeability, and because of that, there is, as you said, there is no reluctance. If we want to have some flux flow through it, there is nothing to resist against that flux. So first of all, ferromagnetic core has infinite permeability. What about losses? How many losses we are having in an ideal core? Zero. So no hysteresis and or any current losses. It's an ideal core. There is no loss here. The other assumption is that usually we know when we have some windings, the flux, all the flux is not confined to the core. There are some flux also that goes in the air. Because they have leaked out of the core, we usually call them leakage flux. But in this case, because everything is ideal, we assume that there is no such a thing. All the flux is confined through the core. So whatever flux goes through the winding 1 will go also through winding 2, and vice versa. The same amount of flux has linked these two windings. Completely confined within the magnetic material, which is our core, and is thus perfectly linked by both windings. Any question here? Okay, everyone has written. Okay, so now let's go and have the magnetic equivalent magnetic circuit of this transformer that we have here. So for each leg we will have a reluctance and we have a winding here with a current that comes like this. So we have reluctance here and then we have an MMF N1 I1. Here for each leg, for each part of this core we have some reluctance. So we will have RC2 here. But top and bottom are very similar, so we can say both are RC2, and here also for the right and left one. And here we have another winding. If the current is like this, again the direction of the MMF will be like this. Minus, plus, now N2 I2. And flux, let me put this here, RC2 will be something like this, as it has already shown in the figure below, figure 2. So if go ahead and calculate the flux will be N1I1 minus N2I2 over RC1 plus RC2, but in fact we have 2 of each, so we can write it like this. So N1I1 minus N2I2 will be equal to 2 RC1 plus RC2 phi. But as your friend mentioned, here in an ideal core, reluctance is almost 0. So we know that mu r is very, very large. So RC1 and RC2 is almost 0. In that case, N1I1 minus N2I2 will be equal to 0. Let me put it like this. The net MMF is 0, and it makes sense. When you have an ideal core, you don't need any MMF to push the flux through the magnetic circuit. So net MMF should be 0 in an ideal core. So N1I1 will be equal to N2I2, or I2 over I1 is equal to N1 over N2. What is happening here? It says the ratio of the currents is related to the turn ratio of the windings. We can change the level of the current by changing the turn ratio of the windings. That's what we are looking for. We wanted to, in some cases, decrease the level of the current, and in some cases, increase it. And it can simply happen by the turns ratio of the windings. And it says the windings that has more number of turns will have the lower current. Says the winding with a larger number of turns carries a smaller current than the other winding, and vice versa. So we can change the level of the current. Okay. What we can say about the level of voltages? With the Amperes law and the equivalent magnetic circuit, which is a form of Amperes law, we find the relation between the current. Let's use the other law that we have. So we find that I2 over I1 is equal to N1 over N2. But we want to find the relation for the relationship for the voltages. Now we use Faraday law. We know V1 is equal to N1 d phi over dt. For the other windings, we know V2 is equal to N2 d phi over dt. Now you can see why we made the third assumption. Why? We made that assumption that the same current goes through the both windings, the same flux, because now these two flux should be the same. Now we are going to use that assumption to find the relationship between V1 and V2. It says V2 over V1, it is equal to N2 over N1. Other words, the winding with the larger number of turns will develop the larger voltage. And you can also here see why we cannot use it in a DC system. If the current was DC, this was direct current, I was constant, d phi over dt was 0. No voltage will be induced at any side. That's why Mr. Edison cannot use the same pattern, the same equipment in the DC system that he has. Why only the AC system can benefit from these transformers? Because this flux should be fluctuating. That's why the voltage and the current in your homes are sinusoidal. Okay. So the other important thing that we saw, that neither n1 or n2 is important, but the turn ratio is important. So we usually introduce new parameter a equal to n1 over n2, which is the turns ratio. So if we want to rewrite the equation, we will have v1 over v2 is equal to a, or equivalently, v1 is equal to a v2, and I1 over I2 is equal to 1 over a, or equivalently, I1 is equal to 1 over a I2. So the number of turns are not important for us. The turns ratio are important for us. I think we can have a break now for 10 minutes. We continue after that. Let's continue with an example. We have this ideal transformer here connected to a load and to a source. The other thing that you should notice, we have some numbers up over the transformers. They show the turns and the turn ratio. When they said 120, it doesn't mean that exactly the number of turns are 120. They may be 1,200, because we are just interested in the ratios here, not the exact number of the windings. And we usually, as I said, we show the turn ratio like that. And it was no problem if you want to try to show it 5 with 5 and 1, because it's just the ratio that matters for us. So V1 and I2 are given to us, and we are asked to calculate V2 and I1. So A, the turn ratio, is N1 over N2. It is equal to 100 over 20, which is equal to 5. Then from the equation we just introduced, V2 is equal to 1 over A V1, which is equal to 1 over 5 multiplied by 120 square root of 2 cosine 377t is equal to 24 square root of 2 cosine 377t. And I1 is equal to 1 over A I2 is equal to 1 over 5 multiplied by 10 root of 2 cosine 377 minus pi over 6 will be equal to 2 square root of 2 cosine 377t minus 5 over 6. So one thing that we can see, the voltage at the primary side, at the source side, is higher than the secondary side, at the load side. But the current at the secondary side, at the load side, is higher than the primary side, than the source side. The other thing that you can see here is this 377T, as we said, we use the transformers in the AC system, not the DC systems. And this omega is in fact the angular frequency of the system. We are going to see this number very much because it's the angular frequency of the North American AC system. You can see for North American power system. So omega is equal to 2 pi f is equal to pi, here is 60 hertz, will be equal to 377 radian per second. Is it the same all around the world? Frequency 60 hertz? Actually, most of the countries in Europe, Middle East, most of the Asia, they are using the other frequency, which is 50 hertz. So in that systems, omega is almost 340 radian per second, which let's say European, but is in fact almost all of the world except North America and some parts in Japan and some other world, but mainly most of the world is on 50 hertz system. Okay. Very good. Can I go to the next slide? Okay. So we find these two equations that V1, V2 is equal to N1 over N2, which is equal to A. And we said I1 over I2 is equal to N2 over N1, which is equal to 1 over A. Let's multiply the left side of these two equations. So V1, V2 multiplied by I1, I2 will be equal to A multiplied by 1 over A. This one is A and this one is 1 over A will be equal to 1. So it means V1I1 is equal to V2I2. But what is V1I1? What is V1I1? Any idea? Pardon? Power. Exactly. It's the power that we are giving to the generator. What is P2 V2I2? Yep. Is the power that we are giving to the load. It means the same power that source gives to the transformer gives to the load. No power is consumed or generated inside an ideal transformer. The only thing that is changing inside the transformer is the voltage and current level. No power consumption or generation. An ideal transformer is very much similar to a lever. In an ideal lever, no power is generated or consumed. Only the force and the velocity of both sides of the lever are different. The side with the longer leg will have higher force and lower velocity. Here, the side with the higher turns have higher voltage and lower current, but the power remains the same. Transformers do not generate or consume power, at least the ideal one. That's why P1 is equal to P2. In reality, however, there are some losses. P2 is not exactly equal to P1. But in a well-designed transformers, P2 remains very close to P1. A well-designed transformer is very efficient transformer. That's the importance of the Tesla invention. That's why they won the game. Because with the very small losses, they could convert the energy and save a huge amount of losses over the transmission. It is a very simple construction. At the same time, it's a very efficient equipment. Later in this course, in the next session, we will talk about the efficiency of the transformer. And you see it's really high efficiency. So the important equation here is P1 is equal to P2, at least as long as we are talking about ideal transformers. We previously find all this equation based on this figure, and by our magnetic circuit, we find that N1I1 minus N2I2 is equal to 0. Net MMF is 0, and V1 over V2 is N1 over N2 by Faraday's law. But all of them was based on the circuit that we have here. What if the winding was wound in other ways? For example, if this winding was wound this way, then instead of N1I1 minus N2I2, we had N1I1 plus N2 over N2I2. Then we will get different relationship. It's equal to minus N2 N1. So it seems we need that physical structure each time. We want to see how they have won. We also want to make sure that the polarity is chosen correctly. If we choose V2 in different polarity, with opposite polarity, also the second equation is going to change. But we said from very start, we want to get rid of this physical structure. We want to have the symbols. But our symbols cannot show this, so we need some modification. We need to enhance the symbols that we have that can reflect, that can show this important feature from our system. And we do it very simply, just by adding two dots and considering two simple rules. In all of these figures, in all of these four figures, we have these two relationships. V1 over V2 is equal to N1 over N2, and I1 over I2 is equal to N2 over N1. We add two dots here. Can you see them? One dot here, one dot here. Similarly, you can see the dots in each of them. And there are two simple rules for using these dots. First set, if the current enters a dotted terminal, it will exit the other dotted terminal. What does it mean? See here, I1 enter the dotted terminal. So the other current should exit the other dotted terminal, like this. If we want to keep the I1 over I2 equal to N1 over N2. Here, I1 enters the dotted terminal. See the dot here? Then the other one exit the dotted terminal. Or vice versa. See, here I2 enter the dotted terminal, I1 exit. So let me show it with the I1 enters, then I2 exit. Again, I2 enters the dotted, the other one should exit the dotted. That's simple. What is the second rule? It says the voltage of the dotted terminals in respect to undotted terminals have the same polarity. So see what has happened here. Here the dotted terminal in this one is positive, so the other dotted terminal should be positive. Here again, dotted terminal, see it, is positive. Now the other dotted terminal should be positive. If you want to have the equation of V1 over V2 is equal to N1 over N2. Similarly here, the dotted terminal is positive, the dotted terminal is positive. Very simple. So we are not going to draw the physical structure each time. We just use the symbols with these dots. And then we know how to find the direction of the current and polarity of the voltages. Everyone done here? So what does it exactly mean? Said if you want to keep the relationship of V1 over V2 equal to N1 equal to N2, the dotted terminals should have the same polarity. In this case, even not the sinusoidal, for any signals, the V2 always have the relationship of V1 over V2 over N1 over N2. It's positive. The relation is kept the same because of the rule that we have used for the dotted one. Similarly here. Even for trapezoidal is the same. But if you don't use the law, see what has happened here? The dotted terminals are here. One is positive, but the other one is negative here. So now the relationship doesn't hold anymore. In fact, it should be negated. In this case, we'll have V2 like this and V2 like this. Because the dotted terminal doesn't have the same polarity. So the dotted terminal always should have the same polarity to keep that relationship and use it.
In the previous rule, did you say that if the dot is, for example, on the right side, there's a dot, so the positive terminal should be at the same side as the dot?
Can you repeat it?
Shouldn't V2 be positive on the top and negative on the bottom?
Oh, you mean in the below figure? Yes, so here you're right. Here we don't use the dot convention. So there the relationship is not holding anymore. Instead of V1 over V2 equal to N1 over N2 is equal to minus N1 over N2. If you want to hold that equation, you should use the dot convention. You're right. In the below figure, we haven't used the dot convention, and the result is the negate of what we expect. Everyone's okay here? So, if I want to summarize it, said the polarities of the voltages of the voltage at the dotted terminals agree. It means if this terminal is positive, this terminal will be positive, or vice versa. This dotted terminal have the same polarity. So if I want to describe more, said when a voltage with positive polarity appears across coil 1, the voltage across coil 2 is also positive at the dotted terminal. The same is true for negative voltage. Everyone's okay here? Can we go to the next slide?
I just have a question about like the number of windings. You said that it's really the ratio of the windings that's important, right? Not the number of windings themselves.
Number of the turns, yeah.
So then, in a practical sense, wouldn't it be better to have the least number of windings as possible to reduce the resistance through the windings? So then how do you actually determine the number of windings that you want to use? Like what's the factor there?
When I send the yeah, so from the power transfer point of view, you are so right. So the turn ratio is not important and seems to have less resistance. You need to have a few as low as possible number of turns. When it comes to the practice and practical points of making a transformers, usually you make some problems with the leakage fluxes and not a good flux go through it, so you cannot use that low number of the windings. They usually even go to the much larger numbers, and they try to use the winding in a way to make sure that the leakage is minimum there. So no, you are right about the resistance point of view, but because of some other practical points like the leakage and the flux that go through, they usually cannot go with the so low number of the fluxes, and they usually go even with a high number of the turns for the windings. So in short, it's a practical problem for the making the transformer. Okay. Is dot convention only convention that we use? No, there are other conventions that also have been used, especially for large transformers in the power system. So in those large transformers, usually they call the high voltage side with the H. So here is high voltage side, and they use X to show the low voltage side. And then instead of dot, they use numbers. The terminals with the same numbers can be considered the dotted terminals. So these transformers, if we want to use the dotted convention, it can be like this or like this. Both are correct. The balls that have same numbers can be considered the dotted terminals. If you see such a convention, you can simply change it to the dot one if you want. But for most of the case, we stick to the dotted convention.
Dotted one, usually?
They just use 1 and 2, and you can use both of them. They're equivalently correct. No difference between them. Okay. The last thing about the dotted terminals is that, okay, what if someone give us the physical structure and ask us to determine the dots? How can we do this? In fact, it's relatively simple. So we use it in 5 steps here. One, put a dot on one terminal of one of the windings. So here, for example, let's put the dot here. We can use any other terminals. Then let the current enters that terminal. So it will be like this, and it comes out like this. Three, find the direction of the flux flows into the core because of this current. So what will be the flux that this current will force into the core? We can use the right hand rule. It's like this, so the direction of the flux will be to the up. So we will have flux like this. Then find the direction of the current in the other winding which generates flux in the opposite direction of flux in 3. So we want a flux in opposite direction. We want such a flux. Sorry. Let's call it phi 2. Let's call it phi 2. How we can generate such a flux if we want it? We need such a current to generate such a flux using your right hand. So the direction will be like this. Is it okay to everyone up to this point? Finally, put the dot on the terminal from which the current exits. Bless you. That's simple. So we find the dot convention. Everyone is okay? Everyone can understand this? Can someone comes and do the other one? Anyone can come and do the other one? Okay, no pressure. Should I leave it to you to do it at home or should I do it here? At home?
Yes.
Okay. Any objection to your friend? Should I leave it at home? Pardon? Okay. We have different opinion here. I think most of people don't vote. It's like the election that we are having 2 weeks. Can you want to vote? Can I do it now or you want to do it home? Now? Okay. I hear more now, but I'm not sure. Okay, let's do it. So first of all, we put dots. Do you want to do it? Do you want to do it here now? Come here.
Me?
Yes.
Can I do it from here? Just like.
Yes, sure.
Okay, so going in, put 1 on the top is a dot.
So put a dot here. Is good?
Yeah, and then coming out of coil 2 on the bottom is a dot.
Oh, you find the dot for, okay, you have done it. So you said this, the other dot is
Down right corner. Yeah.
Yes, you're right. So let's follow the steps. Put the dot at the terminal, any terminals, put it here. Then the current, let enter that terminal, like this. Then use the right hand and find the flux direction. It's very similar up to this point to the other one. So flux will be like this. Then you need a flux in opposite direction. Let's call it phi 2. And from the right-hand rule, to generate such a flux, you need such a current. It means it enters here and exit here. And as your friend said, you need a dot here. Okay. Everyone's okay here? You can use the same rule if you have even more than 2 windings. Just start with 1 and find the dot for each winding one by one. So, enough of the dot convention. It's not that complicated at the end. Let's go to the more circuit analysis. So we have all the coupling and transformers, and it usually doesn't allow us to do the circuit analysis simply. So in most of the cases, as much as we love the transformers in the real world, when it comes to the analysis, we want to get rid of them and replace them with something else. So here we have N1 over N2, the transformer that we have. We can also write this as A to 1 because only 10 ratio are important for us. So what we are interested is that remove the transformer and load, and instead of that, put one load here. We call this Z prime. It's not exactly the Z. And in fact, it is the reflected load when the load is reflected to the other side. So I1 and V1 is the same, but here we have V2 prime. We reflect the voltage of the V2 to the other side and add a prime there. Is AV2. And AV2 is equal to V1. We also reflect the current other way. And because it is reflected is I2 prime. And it's equal to 1 over A I2. If you calculate the V1 over I1, we can write this one as A V2 over 1 over A I2. It is equal to A2 V2 over I2. But what is V2 over I2? What's V2 over I2? Remember?
Not going to be Z prime.
V2 over I2 is Z. Am I right? V2 I2, the load. So this one is Z prime. It is equal to A2 Z. So V2 over I2 is Z. If you look at this side of the circuit, this part, see, we have V2, I2 and load. So in fact, this reflected load is the load that primary sees. if you sit at the primary point, the load that you see is Z prime, is not Z, and it's the impact of the transformer. We can reflect the other load to this side, and then we have this relationship. So a load and a transformer can be replaced by a reflected load whose impedance is A square times the original impedance. Okay. V2 prime is equal to AV2, yes. Because V2 prime is equal to V1. See, we have reflected it. See, there is nothing between them. There is no resistance between them. They are connected in resistance-less wires. So V1 is equal to V2 prime here, because there is nothing between them, and V1 is AV2. Or in other words, when you reflect everything from the secondary to the primary, voltage is multiplied A times, and the current is reduced by 1 over A. But for the impedances, they are increased by A2. Did you get it? Is it clear now? But this is not one way. In fact, you can also, instead of bringing the load in this side, you can also take the source to the other side. We are going to talk about this in detail in a few minutes. So, it said it is impedance. I hope you remember impedance from your previous courses, but it's short Z. It's equal to R plus Jx. R is resistance, X is reactance, and X is used for representing both inductance and capacitance. So X can be XL is equal to 2PFL or L omega, or if it's a capacitance is XC and it is equal to 1 over 2PFC or 1 over C omega. So Z prime, which is equal to A to Z, so R prime plus JX prime is equal to AR2 plus A2R A2X. So we can say source sees A2 times of the load resistance. See, here we have this reflected load. That is the load that we see from the source. If we want to talk about in detail about the resistance and reactance, source see A2 times of the resistance and A2 times of load reactances. So for inductances, that relationship is linear is also A2 times, but for capacitance is 1 over A2. This is because XC has a reverse relationship with the reactance. So if you want to bring the capacitor from one side of the transformer to other side, if you want to reflect it, take more care. It's a bit different with the resistance and inductance. That's the whole point I want to make here. Okay. I think some examples can help us to understand everything better. So assume an ideal transformer. So here we have this ideal transformer. What will be the circuit transferred to the low voltage and high voltage sides? As I said, this reflecting is not a one-way street. You can reflect from the load side to the source side, or vice versa. You can reflect the source side to the load side. Now, the difference is that we use the inverse parameters. If they was A2 times, now if any resistance, every impedance you bring here is 1 over A2, 1 over A squared. Okay. Let's start with the low voltage side. So here we have N1 and N2. We can set is 1 and it is 5. So the low voltage side, in fact, is the source side. So because we reflect everything to the load side, to the source side, to the low voltage side, nothing there is changing. It remains very much the same. So we have 10 volt and we have 2 millihenry. Here we have, let me start from a bit below, sorry. To millihenry. So here we have V1 and here I have I1. Nothing has changed because we want to reflect everything to this side. This side remain intact. But the changes start from right here. We want to get rid of the transformers and reflect everything to this side. So then we need to reflect the V, take the V2 and reflect it to the other side. So we will have V2 prime, which is equal to 1 over 5 V2, because we have reflected to the other side. And for reflection, we use the A. And now also current is reflected. Because we are reflecting to the low voltage side, the current will increase, equal to 5I2. Then let's continue from here. The next element we will see is our capacitors. It said the capacitors change by 1 over A squared. A is 1/5. So 1 over A squared will be 20 times larger. So we will have 24.5 microfarad because it's a capacitor. Then let's continue. After that, we will see the V3. Let's reflect it to the other one, V3 prime, which is again use the same A. 1/5 V3. 12.5 because A is 1/5, yes? A2 is 1/25. And because it's a capacitor, 1/A squared, so 25 times larger, not 5 times. Then we will see an inductance. Now A2 is 1/25, so we will have 0.12 Henry. Our capacitor has increased, but our inductance is decreasing. Also, we have IL. We need to reflect that too. We have IL prime, but because we take it to the low voltage side, the current will increase. 5IL. Let's continue. Then we have a resistor. Again, very similar to inductance. A is 1/5, A2 is 1/25. So we will have 1.6 kilo. And we have a current here, IR, because it's reflected prime, and now it's equal to 5IR. So we reflect whole the circuit from the low voltage side, from the high voltage side to the low voltage side. Is everything clear here? The voltages are multiplied by A, which is here is 1/5. The current is divided by A, that because it's A is 1/5, they will be multiplied by 5 here. The impedance I multiply by A square. A is 1/5 again, so A square will be 1/25. Is it clear here? Okay. The next part asks us to take the source and the low voltage side to the high voltage side. As I said, it's a two-way street. Go ahead. Because I'm recording is a little bit hard. Do you have a question? I can answer you. Okay, can you come after the class? I will show you the circuit. Yeah, sorry. Okay. So let's take everything to the high voltage side. This time, low voltage side remain intact. So everything here is as before. We have 300 here. We have 40k ohm here. 0.5 microfarad here. We have IR, IL, I2, and we have V3 and V2. Now we want to reflect from the low voltage side here. So the first thing that we will have, if come this side, we will have I1. Now we will have I1 prime. A is 1/5, and here should multiply by A, so it will be 1/5 I1. In other words, we are coming to the high voltage sides. We expect the current reduced because the power is constant. But for the voltage, V1 prime is equal to 5V1. Then we have this inductance. Now, because we are taking to the other side, we should use 1/A2. So it will be 50 millihenry. And finally, we have the source is 5/10 equal to 50 volt. Everyone's okay? Go ahead.
So when we were doing the low voltage side, A was 1/5. Then when we do the high voltage, A is 5.
Yeah, because we do it exact the opposite thing. But don't use A is 5 because A is always 10 ratio 1/1/2. But yes, the scale that you use is exactly inverse. So your transformer is somewhere like here. When we remove it. And now we have one circuit. The analysis is much easier. Everyone's okay? Just one more simple example and we are done today. Do you remember we talked about that maximum power transfer and maximization of the power and load matching? Here is one example. So a speaker of 9 ohm resistive impedance is connected to a stop-by of 10 volt with internal resistive impedance of 1 ohm. As shown in the figure, determine the power absorbed by the speaker. This part is very simple. It's nothing with the transformers. So you have 10 volt RMS here. This is the 1 ohm that we have here, and this speaker is said it's 9 ohm. So here is VS, here is VL. So VL is equal to 10/9 plus 1 multiplied by 9 is 9 volt. It's a simple circuit analysis. There's nothing special here. So PL is VL2 over RL. It's 9 square over 9 will be equal to 9 watt. So without transformer, 9 watt is transferred to the other side. Any question here? Simple circuit analysis. Okay. The final part asks us, we want to maximize the power transfer, so we use a transformer with a ratio of 1:3 in a very same circuit, as you can see here. And it asks us to calculate the power that this time is taken. And so here is the circuit. 10 volt, 1 ohm. Here is our load. These are the same. The only thing that has changed this time we use a transformer. And the ratio is 1 to 3. So let's move everything to the load side. So the load will not change. It's 9 ohms. And the voltage here is VL. But then this 1 ohm will change. 3 squared will be 9 ohm. And then the source will change to 30 volt. So here we have S prime. So these are the source and cable resistance transferred to the secondary. The rest is very simple circuit analysis we already have. Very similar to that. So VL is equal to 30 over 9 plus 9 multiplied by 9 will be 15 volt. PL will be equal to VL square over RL will be equal to 15 square over 9 will be equal to 25 watt. It's almost tripled. Everything is same, we only use the transformer. It's one of the applications we mentioned for the transformers. But you see the powers here, 9 watt and 25 watt. They are very small powers, ratings, in comparison that what we use to work in the power system usually. So that's why it's usually used in electronic and in communication, not very much in the power system and application we are interested in. And the other thing is that we now take everything to the secondary. You will find some example that we take everything to the primary, except the time that has been very explicitly have mentioned where you should transfer your circuit or some very special cases. It's your choice. You should see which one is better. You take everything to the load side, to the secondary side, or primary side, and depends on the application. Here we are very much interested in the load. The load was important, so we take everything to the secondary. There are applications you take everything to the primary. I think that's enough for today. We will continue transformers next week. Thank you.